Rock-forming minerals constitute the fundamental components that make up Earth's crust, serving as the essential building blocks of our planet's solid foundation. These minerals form through various geological processes, including crystallization from molten magma, precipitation from mineral-rich solutions, and transformation under intense pressure and temperature conditions. The most abundant rock-forming minerals include quartz, feldspar, mica, amphibole, pyroxene, and olivine. Each mineral possesses distinct chemical compositions and crystal structures that determine the characteristics of the rocks they create. Understanding these minerals is crucial for comprehending how igneous, sedimentary, and metamorphic rocks develop and evolve throughout geological time periods. Minerals serve as Earth's fundamental building blocks, forming the essential components of all rock types. These naturally occurring, inorganic solids possess specific chemical compositions and crystalline structures that create igneous, sedimentary, and metamorphic rocks. The mineral composition within rocks directly determines their physical and chemical properties, including hardness, color, luster, and responses to geological processes. This relationship proves vital for accurate rock classification and understanding geological history. Studying rock-forming minerals provides crucial insights into formation conditions, enabling geologists to analyze Earth's dynamic processes, identify valuable resources, and comprehend our planet's continuous evolution throughout geological time. Silicate minerals represent the most abundant mineral group on Earth, comprising over 90% of our planet's crust. This dominance stems from the high abundance of silicon and oxygen, the two most common elements in Earth's composition. The fundamental building block of all silicate minerals is the silicon-oxygen tetrahedron, a pyramid-shaped structure with silicon at its center, surrounded by 4 oxygen atoms. How these tetrahedra connect and combine with other elements determines the specific properties of different silicate minerals. Common examples include quartz, feldspars, micas, amphiboles, pyroxenes, and olivine, which form the foundation of nearly all rock types found globally. Silicate minerals form the foundation of Earth's crust, with 6 key groups dominating geological formations. Quartz, composed of silicon dioxide, ranks as one of the hardest minerals at 7 on the Mohs scale and comprises 12% of the crust. Feldspars represent the most abundant group at 60%, including plagioclase and orthoclase varieties, essential for rock classification. Mica is split into thin, flexible sheets, with light muscovite and dark biotite being most common. Amphiboles like hornblende form prismatic crystals, with distinctive 60-degree cleavage angles. Pyroxenes appear in dark, igneous rocks, while olivine crystallizes first from magma and dominates the upper mantle. Non-silicate minerals form a diverse group distinguished by their complete absence of silicon-oxygen tetrahedra structures. While less abundant than silicate minerals, they hold tremendous geological significance due to their formation through varied processes including evaporation, precipitation, and biological activity. These minerals provide crucial economic resources, from metallic ores to essential construction materials and everyday products like salt. The major classes include carbonates such as calcite, which forms limestone and marble from marine organisms, sulfates like gypsum, used in plaster and drywall, and halides including halite, our common table salt formed from evaporating salt water. Non-silicate minerals play crucial roles in geology and industry, with 4 key examples demonstrating their diverse properties and applications. Calcite, composed of calcium carbonate, forms the foundation of limestone and marble, readily fizzing when exposed to dilute hydrochloric acid. Dolomite contains additional magnesium and reacts more slowly with acid when powdered. Gypsum, a soft sulfate mineral, proves essential in construction through plaster and drywall production due to its unique hardening characteristics. Finally, halite, commonly known as table salt, forms through seawater evaporation, crystallizing in cubic structures and dissolving easily in water, making it vital for both culinary and industrial purposes. Minerals serve as Earth's fundamental building blocks, combining in countless ways to create the diverse rock types spanning our planet's crust. The specific mineral composition and formation conditions determine each rock's unique characteristics. Igneous rocks form from cooling molten material, with cooling rate affecting crystal size. Slower cooling produces larger crystals. Sedimentary rocks develop through accumulation and compression of sediments from existing rocks, minerals, or organic matter, often displaying distinct layering and fossil preservation. Metamorphic rocks emerge when existing rocks undergo transformation through intense heat, pressure, or chemical processes, fundamentally altering their original mineralogy, texture, and composition. Mineral composition fundamentally determines every rock's physical and chemical properties. The types and proportions of minerals directly influence characteristics like hardness, color, and weathering resistance. For example, quartz-rich rocks achieve significantly greater hardness than talc-dominated formations, while iron impurities in hematite create distinctive red coloration. Chemical stability varies dramatically. Quartz resists weathering exceptionally well, whereas calcite dissolves readily in acidic conditions. Silicate minerals dominate Earth's crust, comprising over 90% of crustal composition. This dominance stems from oxygen and silicon being the most abundant elements at 47 and 30% respectively, forming silicon-oxygen tetrahedra that link together creating diverse silicate mineral structures.